I have been thinking about silicone in a whole new way recently, especially after looking at a can of slippery silicone spray right next to a tube of sticky silicone caulk. It is wild, right? Both are called silicone, but their uses and textures could not be more different. How does one material manage such incredible versatility? It is a question that delves deep into the fascinating world of chemistry, revealing how subtle changes at the molecular level lead to drastically different everyday products. Let us demystify silicone together really quickly. To truly understand it, we need to go back to its roots. Silicone is not just one thing, it is actually a whole family of synthetic polymers. And critically, it is not the same as silicon, the element. Think of silicon as the raw ingredient, like flour, and silicone as the baked good, like a cake. This distinction is the very first step to unlocking its secrets. The key is understanding silicone's unique backbone. Unlike organic polymers, which are based on carbon chains, silicone polymers have a backbone made of alternating silicon and oxygen atoms. This silicon-oxygen CO chain is incredibly strong and flexible, forming the core of all silicone materials. This fundamental structure is what gives silicone many of its remarkable properties, setting it apart from plastics and other materials we commonly use. What is fascinating is that attached to these silicon atoms are organic groups, most commonly methyl groups. These organic side chains are crucial because they are what allow chemists to fine-tune silicone's properties. By changing the length, arrangement, and type of these side groups, manufacturers can create an astonishing array of materials, each with unique characteristics tailored for specific applications. It is like adding different toppings to that basic cake. Imagine if silicone worked like this. Picture those silicon and oxygen atoms as the main spine of a Lego structure. The organic side chains are like the different colored Lego bricks you attach to the spine. You can build a short, smooth structure that slides easily, or a long, intricate one that interlocks with others, making it rigid and sticky. This simple analogy helps visualize how the molecular architecture dictates the macroscopic properties. So, how does this chemical blueprint explain why one silicone is a super slippery lubricant while another is a super sticky adhesive caulk? It all comes down to two main factors: the length of these polymer chains and whether or not they are cross-linked. These subtle modifications are where the real magic happens, transforming the fundamental silicone structure into incredibly diverse materials. Let us begin with the slippery stuff, like that silicone lubricant spray. It starts with very short silicone polymer chains. Think of them as individual, unattached strands of spaghetti. Because these chains are relatively small and do not bond to each other, they can slide past one another with very little friction. This molecular freedom is what gives silicone oils and lubricants their characteristic slickness and flow. What is fascinating about these short-chain silicones is their incredible slipperiness combined with their chemical inertness. They do not react with most other materials, they resist water, and they have excellent thermal stability. This makes them ideal for lubrication in places where traditional oils might break down, get gummy, or harm plastics and rubbers. Their non-stick properties are unmatched. The result? Silicone lubricant finds its way into countless applications. You will find it freeing sticky drawers, protecting rubber seals, lubricating gym equipment, and even making fishing lines cast smoother. Its ability to reduce friction without attracting dust or degrading surfaces makes it a go-to for maintenance and performance enhancement in a variety of industries and household tasks. Now imagine those short, unattached spaghetti strands suddenly becoming much longer. This is our first step towards the sticky caulk. These longer silicone polymer chains are naturally more viscous, meaning they flow less easily. They start to entangle with each other, creating a thicker, more substantial material, even before we introduce the next crucial step. The big reveal is cross-linking. For silicone caulk and adhesives, these long polymer chains are not just intertwined, they are chemically bonded together. Think of it like cooking those spaghetti strands until they are firm, and then using tiny, invisible chemical stitches to sew them into a giant, flexible net. This network structure is incredibly strong and resistant to deformation. Progressing from there, This cross-linking process is often initiated when the caulk is exposed to moisture in the air. This is why you usually have to apply silicone caulk quickly, and it needs time to cure. During curing, a chemical reaction occurs, forming those strong bonds between the polymer chains, transforming it from a gooey paste into a durable, elastic solid. Ultimately, a cross-linked silicone forms a tough, elastic material. This is what gives caulk its sticky adhesion and its ability to seal gaps, resisting water, temperature changes, and UV radiation for years. It is not just sticky, it is also incredibly flexible, allowing it to move with building materials without cracking, making it perfect for sealing windows, doors, and bathroom fixtures. The process begins with the raw material, silica, essentially sand. This abundant compound is heated to extremely high temperatures with carbon to produce elemental silicon. This is an energy-intensive process, but it is the fundamental first step in creating the building blocks for all silicone materials, separating the silicon from its oxygen partners. From there, the silicon undergoes further chemical reactions, most commonly with methyl chloride. This creates compounds called chlorosilanes, which are the direct precursors to silicone. This step introduces those organic methyl groups that will eventually hang off the silicon-oxygen backbone, making the material organic-like while retaining silicon's unique properties. The polymerization process follows. The chlorosilanes are then hydrolyzed and condensed to form siloxane chains. This is where the silicon and oxygen atoms link up, forming the long, repetitive backbone. By carefully controlling the reaction conditions, manufacturers can dictate the length of these chains, directly influencing whether the final product will be a liquid, a gel, or a solid. The ultimate insight is that silicone is not just a two-trick pony. We have talked about lubricants and caulk, but the range is vast. Think about silicone gels used in medical implants for their soft, tissue-like feel, or the heat-resistant silicone bakeware that is flexible yet incredibly durable. Each form is a testament to the precise control chemists have over its molecular structure. Consider how silicone has transformed medical devices. Its biocompatibility, meaning it is not rejected by the human body, makes it indispensable for everything from pacemakers to catheters and, famously, breast implants. This remarkable property stems from its inertness and stability, allowing it to perform critical functions without causing adverse reactions. Adding to that, its incredible heat resistance means it is perfect for the kitchen. Silicone spatulas, baking mats, and oven mitts can withstand high temperatures without melting or leaching chemicals, making cooking safer and easier. The silyl bond is just incredibly stable even when things get hot, unlike many organic polymers that quickly degrade under heat. What we discover is silicone's crucial role in electronics. It is an excellent electrical insulator and provides protection against moisture, vibration, and extreme temperatures. You will find it encapsulating sensitive circuit boards, sealing wiring, and forming keypads, extending the life and reliability of our electronic gadgets, from smartphones to industrial machinery. Then something interesting happens when silicone makes its way into beauty products. Silicones like dimethicone are prized for their ability to create a smooth, silky feel in shampoos, conditioners, and lotions. They form a breathable barrier on skin and hair, locking in moisture and providing slip without feeling heavy or greasy. It is a touch of luxury, engineered at the molecular level. Looking closer, we also consider the environmental aspect. While silicone's durability is a massive advantage in its applications, it also means it is not readily biodegradable. It lasts a very long time. This is a topic of ongoing research, with efforts focused on making silicone production more sustainable and exploring recycling methods for end-of-life products to minimize its environmental footprint. The key is the precise tailoring of properties. Manufacturers do not just make generic silicone, they fine-tune everything from chain length to the degree of cross-linking and even the type of organic groups attached. This allows them to create silicones that are specifically designed for high-temperature gaskets, super soft baby bottle nipples, or robust construction sealants. Building on that, various additives also play a huge role. Fillers like silica powder can increase strength and stiffness. Pigments give silicone its color. Catalysts initiate the curing process for products like caulk. Each additive is carefully chosen to enhance specific performance characteristics, turning the basic silicone polymer into a high-performance material. And here is the cool part: quality control is paramount. Given the precise nature of silicone's properties, rigorous testing is done at every stage of production. This ensures that a silicone intended for medical use meets stringent purity standards, or that a construction sealant will perform reliably for decades. Consistency is key to unlocking its full potential. Let us examine the unique role of silicon itself. The element silicon, a metalloid, forms the core of silicone's impressive durability. It is just below carbon on the periodic table, sharing some similarities but also crucial differences that make silicones distinct from their carbon-based organic cousins. What becomes clear when comparing silicon to carbon-based polymers is the strength and stability of the silicon-oxygen bond. This bond is much stronger than the carbon-carbon bond in many plastics, especially when it comes to resisting heat and UV radiation. This is a fundamental reason why silicone performs so well in harsh environments where plastics would fail. The thermal stability is a key advantage. Silicone can withstand extreme temperatures, both high and low, without becoming brittle or melting. This property is invaluable in industries ranging from aerospace, where components must perform in vacuum and extreme temperature swings, to automotive applications, like engine gaskets that endure constant heat cycles. The outcome? Excellent water repellency. Those organic side groups, particularly the methyl groups, make silicone hydrophobic. Water literally beads up and rolls right off. This makes silicone an ideal choice for waterproofing sealants, coatings, and even textile treatments, protecting surfaces from moisture damage and preventing mildew growth. Another crucial property is UV resistance. Unlike many organic plastics that degrade and become brittle when exposed to sunlight over time, silicone maintains its integrity. This makes it perfect for outdoor applications like building sealants, solar panel components, and outdoor lighting fixtures where long-term exposure to the elements is expected. Building momentum, electrical insulation is another area where silicone shines. It is an excellent dielectric material, meaning it does not conduct electricity easily. This, combined with its thermal stability and flexibility, makes it a preferred material for insulating wires, cables, and electronic components, enhancing safety and preventing electrical shorts. What this means for you is that next time you encounter silicone, whether it is the slickness of a lubricant or the grip of a sealant, you will understand it is not magic. It is brilliant chemistry. It is the elegant dance between the silicon-oxygen backbone and the carefully chosen organic side chains, all orchestrated to create a material with tailor-made properties for countless applications.